As one of your friends mentioned, we can construct dampers, for example. Let's look at something like a damper, a device like a damper here. Let's say that we have again a piston.
Hocam, may I ask something from the previous part?
Yes.
While we're taking the Laplace of the differential equation, for the y double dot, don't we need to also add minus f0, minus s f0?
No, that is the whole point. When you do take the transfer functions, you always assume that the initial conditions are neglected, okay? In the transfer functions, we neglect the initial conditions.
Okay.
Okay?
Hocam, can I ask a question in
Yes.
general? We are neglecting in theory, but in the reality, what are we going to do, hocam?
Well, we are not neglecting. That is the definition. That is the definition of the transfer function. Okay? In reality, you know, the transfer function doesn't exist in reality. It is our construction anyway. It is a tool. It is a tool we use for analysis, kind of. Okay? Okay. This is the device, the piston. Let's say this is Q1, Q2. This is X. This is Q, goes through here. This is the hydraulic resistance, as you might remember. Yes, this is P1. The piston has a mass. It has a mass of m and an area of a. We apply a force P on the piston, F on the piston. P1 and P2 are the forces on the two faces of the piston. We would like to derive the equation. F is our input and X is our output. Let's see what kind of a relationship we get out of this. So what happens here is that when you push this piston, the fluid gets displaced and goes through this port and passes through this fluid resistance, and it loses some of its energy, therefore its pressure drops and goes to the other side and pushes the piston again. Well, it doesn't push, but well, the pressure here becomes P1. So the pressure here is P2, here is P1, and I guess if the flow is in this direction, P2 must be greater than P1. So the continuity equation says that Q is equal to A times X dot, right? Flow rate is equal to that. That's one equation. Then you have P2 minus P1 over R is equal to Q, is the fluid resistance equation. So these are kind of equal to each other. can say delta P to P2 minus P1. Another thing is you have to sum up the forces on the piston. What are the forces? Let's see. You have the F force. You have P1A on one side. P2A on the other side. This has to be equal to rather, or I should say M. I use a capital M, so let's use a capital M. So this is Newton's second law. So using these three equations, actually we can derive our equation. Q is equal to AX, so we can eliminate Q from here. AX dot is equal to P2 minus P1 over R. So P2 minus P1 will be equal to R A X dot, right? And F minus P2 minus P1A is equal to mx double dot P2 minus P1 is F minus this R A squared X dot is equal to mx double dot, and we carry it to the other side, mx double dot plus R A squared X dot is equal to F is our equation, F of T. Okay, if F is the input and X is the output, the transfer function, you just take the S terms out of it, the transfer function. X of S divided by F of S. I'll just write it if you don't mind. You can derive it yourself. 1 over something like this. No. Yes. Okay. Now look at this one, this equation. If M is negligible, then you can say that F of T is approximately equal to R squared A X dot. And since this is a constant, F is equal to some constant which we can call B times X dot, okay? And as you see, this is a damper equation, hydraulic damper. So it dissipates energy. If the mass is not negligible, then, well, there is an extra term to it, the mass term, the inertia term to it, but you get the idea. If the mass is not very important, if the mass of this damper is small compared to other forces, or if the accelerations are small, you can treat this as a damper. But in general, this device, as you see, dissipates energy. So it acts like a hydraulic damper. Okay? That is the whole idea in the hydraulic systems. Usually in the hydraulic systems, you use balances of force and the continuity equation, and then substitute them to each other to obtain the transfer function of the system. Any questions about this? Because this is as much as I will do for hydraulic systems. If not, the final thing we will look at will be the thermal systems. Basically, our main law will be the conservation of energy here. Thermal systems are rather simple. Basically, it says that the heat in minus heat out should be equal to the energy stored, okay, in the system. We will use this. This is our main law. But also we have two things, the thermal resistance, just like in electrical resistance, and we have thermal capacitance. Of course, we are simplifying the thermal systems quite a lot by assuming that there are resistances and so on. But let's look at the thermal resistance first. These are very simplified models of thermal systems, but they are enough for control purposes. You learn about these in heat transfer, but let's say that you have this is the RT, thermal resistance. Let's say that you have on one side of a slab, you have T1 on one side, and T2 on the other side. And if T1 is greater than T2, there is a heat flow. And we know that the heat flow is proportional to this temperature difference, T1 minus T2. If it's proportional, you can write the constant of proportionality as follows, T1 minus T2 over the thermal resistance, Tr. This is like I is equal to delta V over R in electricity, okay? So RT is the thermal resistance. Its value is determined by the conditions. It depends whether you have pure conduction or convection or whatever. All these things is possible. This is the idea of thermal resistance. For example, for the capacitance, you have, let's say that you have a mass of an object like this that is being heated up. There is heat Q coming in. This is the rate of heat. Heat coming in. Heat flow. So it is in watts. This object has a mass of m, and it has a specific heat of C, let's say. Okay? You remember the specific heat from high school or something, right? So the heat coming in is equal to the mass times the specific heat times the time rate of change of temperature. T is the temperature of this object. Now, if you look at it, if you define this MC term as the thermal capacity you get the heat is equal to CT times PT VT. Now, this is the capacity equation. This is related to the electrical C times dV dt. Okay. So the flow is the heat. In the thermal systems, the flow variable is the heat. And the across variable, the thing that causes the flow is the temperature. Let's say the potential variable is the temperature. Okay. In electricity, this is current. This is the voltage. Okay. There is a similarity. Well, you might think that whether there is a thermal inductance, there is no thermal inductance. There is no such thing. So we just have thermal capacity and thermal resistance. Resistance prevents, substances from getting heated up, and substances store energy with the help of their capacitance. One example is the so-called thermometer, for example. Let's say that you have a thermometer inserted to a bath like this. So this is a liquid with a temperature of TB. Now, to this TB, you put a thermometer like this, a mercury thermometer or something like this, so that its rate of expansion, from its rate of expansion, you can find its temperature. And the temperature of the thermometer is T. It is not, in the beginning, it's not equal to the bath temperature. So if you look at the thermometer, excuse my poor drawing again. There is heat coming in to the thermometer, and it heats up the thermometer. Okay, so the Q is equal to mc times the temperature of the thermometer, and this is the thermal capacity, CT of this thing. But this heat flowing to this device, there is also a resistance between the mercury and the temperature of the bath. So, and that resistance is because of the glass of the thermometer. So there is a thermal resistance RT, which is TB minus T over RT. And these two are equal to each other, as you see. So CT times dt should be equal to TB minus T over RT. Connecting the terms together, you can write C. So, this is the differential equation that describes the system. It's a first order system, first order differential equation. And the transfer function, if you want to find it, T of S, the temperature of the thermometer divided by the bath temperature. If you take Laplace transforms and so on, it will be 1 over CT RT S plus 1. Okay. First order. So what happens when you insert this is the time variable, this is the temperature variable, let's say. Let's say the temperature is here, TB, sorry, T, initially it said T of 0 is here, okay? And this is, let's say, is the bath temperature. You know, the thermometer measures not the bath temperature, but it measures its own temperature. So in the beginning, what will happen? It will start like this. It will increase, and it will exponentially come and measure. After a while, it will be, its temperature will be the same as the bath temperature. And this is first order system response, but we will see that later on. Okay. So it's a thermal systems are usually made up of first order systems. They are rather simple. Let's look at another example, home heating. Let's say that you have a very, very simple model of a house. Okay, this is the roof. This is the heater. The house temperature is T. The outside temperature is T naught, T0. Okay. The heater adds heat to the system. And because of the, difference, let's say we are in winter. What happens? There is heat loss to outside, to out. Okay. The house has a certain thermal capacity, obviously. The heat lost Q out is T minus T RT. RT is the thermal resistance of the house. If it's well insulated, this RT will be large so that there will be less heat loss, okay? So it depends whether the thermal resistance is high. If you have a good insulation, RT will be a high number. But we don't really deal with this, how you find this RT and so on. The stored heat is actually is related to the thermal capacity of the house. House has a certain thermal capacity, it has a mass, it has a specific heat, and so on. And there is the Q in. We know that our main equation is, what was it? The conservation of energy, Q in minus Q out is equal to Q stored. So Q in is Q in, we don't know. That is the heat supplied by the heater. Minus Q out is this T minus T naught over RT is equal to CT again collecting the terms. T is the temperature of the house is equal to RT times Q in. Okay. So we have in this system two inputs, as you see. This is the heat input to the system. It raises the temperature. Okay. Just a second. And this is this is the TO is the outside temperature. This is not an input. This is an uncontrolled input, and this is called a disturbance, actually. So the temperature, this causes the temperature to drop. This causes the temperature to increase, let's say. And in the end, we reach a certain balance out of which the system, the heat system, well, the temperature reaches to a kind of a balance, as you see. Okay. Any questions? Thermal systems are like this. You might have multiple thermal systems, like let's say you might have two rooms, for example, like this is one room connected to another room. This is, let's say, C1, CT1 is CT2. Let's say this is RT between them. Okay. Let's say it's RT1, and there is RT2 here. Let's say this is T1, T2. In this case, for example, you can write let's say that you have a heater here. Let me write it in the following form. This is the first room's equation, and you have CT2 I guess I have to first, without doing it, let's do it this way. This is T2, let's say, CT2. There is heat coming in, which is T1 minus T2 over RT1. Heat going out, which is T2 minus T over RT2. This is T2. CT. Let me write it. Is equal to, I'm sorry to cause some trouble with you, if I have caused any trouble. So this is equal to heat coming in minus heat going out. So it is T1 minus T2 over RT1 minus this thing, T2 minus TO over RT2. So this is the second equation. But it can be simplified as follows, but rather we will collect the term CT2 So this is the second equation. You see, the equations are coupled to each other. T2 equation contains T1, T1 equation contains T2. So these are the two equations that relate to each other. You can solve these equations together. In order to obtain a relationship between input Q in and output. Let's say output you might define it as T2 or something like this. TO is the outside temperature. This is again the disturbance, let's say. This is something you don't have control over. This is the input. Output can be T1 or T2, it doesn't matter. You can define either of these as outputs. So such are the thermal systems. If you don't have any questions, that's all I'm going to talk about now. As a matter of fact, for now, I'm not going to, from now, this is the more or less the end of the modeling part of the class. I'm going to solve problems the next time, but I'm not going to do anything else. I think we have done enough for modeling. I have shown you all sorts of different kinds of physical models and then Laplace transforms. And if you have a nonlinear model, how to linearize it, and so on. From now on, we will be doing the response of systems. Once you obtain a system, how do you obtain the response, and also the block diagrams. We will spend more time on the block diagrams. Well, actually, we did some block diagrams, but we will do more. So that's all for now. If you don't have any questions, that's all I'm going to do for today.
Hocam,
Yes.
may I ask about the Q in minus Q out equals to Q store?
Yes.
So like in heat classes, we also had the generation part. So isn't the heater is something like the generator?
Yes, we assume that that is Q in.
Okay.
Yes, generated heat is Q in. You know, here we are doing it very, very simply. In heat transfer, you learn it in a more rigorous way, okay? Here, we are not interested in the details of the heat transfer problem. We do it almost in the, you know, high school knowledge range. But the important thing is we want to model it in terms of the time. That is how it changes with respect to time. We want the dynamic behavior. In heat transfer, you model it very in a detailed manner, but usually in terms of the spatial variable, in the space variables, x, y, z. Here we are not interested. We just take very simple models, but we want the dynamic models. We want the time-dependent models in controls.
Okay hocam.
And that is called the transient models in heat transfer. And usually in heat transfer, you don't really spend much time on transients. You rather most of the time look at steady states, whereas here we spend more time on transients.
Okay hocam. Thank you.
You are welcome. So much for today then. Let me stop the recording at least.